So let's look at an example problem that involves simple internal reflection or total internal reflection and that of the Porro prisms. So let's suppose we have a periscope on a submarine with two Porro prisms. The light will enter the periscope. So we have, periscope looks something like this. And so basically we're going to have light entering. We're going to use one prism to bounce the light downward and another prism to bounce the light this way. So we'd like to reflect this light and bounce it from one place to the next perfectly without losing any of our light. Under normal situations, we need to have a critical angle of at least 45 degrees in order to keep the light trapped inside that Porro prism instead of leaving as it goes from one interface to the next. And so that means if I apply my equation, the sine of 45 degrees has to be equal to N2 over N1, or N air over N of my prism. So I could use this to figure out what my index of refraction of my prism has to be. So if I solve this for N prism, the prism must have an index of refraction of at least 1.41 if it's going to make an effective reflector as a Porro prism. Now in this problem, the question is that the prism becomes submerged in water. So this was the normal situations. Now I'm underwater. And so then the question is, what is my critical angle now going to be? Not going to be the same anymore because it's not the same two materials. So I've got, instead of the light going out into air, I've got water and the prism. And water has an index of refraction of about 1.33, at least for fresh water. Seawater, maybe a little more than that. And then my prism was 1.41. So if I use this then to solve for my critical angle, if the Porro prism is submerged in water, I now have a critical angle of 71 degrees. It's got to strike even bigger than 71 in order to stay in the material. And so if I were to look at, kind of make a drawing of what this is going to look like, the light's going to enter the Porro prism. It's going to strike it at a 45-degree angle here. And because the critical angle now with water on the outside is 71, it's actually going to pass into the next material. It's going to move right through without bouncing and reflecting. And so this won't work. It only works between glass or prism and air. Now I really find this next one very fascinating. So the next time you're in a swimming pool and you dive down to the bottom, try this out yourself. See if it really does this. When you look up, I believe when you look up at the surface of the water from the bottom of the pool, you will see a reflection of the bottom of the pool. There'll only be sort of a narrow window in which you can see the outside of the world. So why is that? Why can we see the palm trees? Looks like we're in Florida or something here, but then the bottom of the pool is reflected at the surface. Well, let's try to draw a good picture to allow us to see what's going on. Instead of drawing your whole body, we'll just draw your eye down here at the bottom. So let's draw some rays of light coming into the pool and what you're going to see. So you should see all three of these rays of light. First one's going to strike, slow down, and go in a straight line. These two are going to bend and travel to your eye like this. You'll see the outside world. But at a certain point, think about our critical angle, the light reaches the critical angle. It's going to move along the interface like this. So you'll notice these are actually the reverse of what we've drawn before, but these light rays are always reversible. So we're going to reach a boundary. We're going to reach a boundary of what you can see. So here is my critical angle, measured from the normal. And so this is going to form a sort of a cone or a circle above me of what you can see. And so within these two red lines, you can see the outside world. But anywhere beyond these two red lines you look, you are only seeing total internal reflection. So everything beyond you are seeing from the bottom. This light came from the bottom of the pool, and this light came from the bottom of the pool. So you see the reflection, which matches nicely with the picture we see of what it looks like in real life. Now the second part of the question asks about being able to see someone that's underwater. So again, this is reversible. We can kind of come down here to the bottom and draw a picture. So here's a person swimming underwater in the pool. And we get some rays of light coming off of him and doing just like what we saw before. And this fellow right here is unable to see the guy underwater because here is the critical angle. And he's got to be somewhere up here above if he wants to be able to look down in the water and see him, but any of the light that would have headed to his eye now is going to be totally internally reflected. On the other hand, this fellow, who's within the critical angle, can look down in the water and see the man below. So out of curiosity, what does this angle happen to be for water and air? Easy enough to find. We got our fast medium over our slow medium. Water about 1.33. We solve this for our critical angle. For fresh water, critical angle is about 49 degrees. So as long as this angle here is something less than 49 degrees away from the normal, you'll be able to see him, but as soon as it strikes more, this guy becomes invisible. Another example of weird refractive behavior in light is that behind the cause of a mirage. So we've seen a mirage. If you've ever seen this appearance of water on the road and maybe a reflection of a car that isn't really there and disappears when you get closer, you're really seeing the refraction of light. Light is coming from the back of this car and it's bending upward towards your eye, as portrayed in this picture here. So we've got two different indices of refraction. We've got hot air where light travels fast, and cold air where it travels slower. So if you imagine like this is the axle of a car and you've got tires on either side, and the cold air is getting bogged down in the mud right here, and this one's on pavement, so it's going to go faster than the other one. It's going to pull ahead and it causes the light wave to bend up to your eye. Now, no offense, but your brain and mine is not able to recognize that light travels in a bent path, and so your brain just traces that back. It sees that light as if it came in this straight line, and it sees the top of the car down here rather than up there. An interesting example of a mirage, you may not have heard of this before, is called a superior mirage, and it's basically the same effect, but a bend the opposite way, or the opposite case. So in this case, you'd be more likely to see a superior mirage in a scenario in the water. So this is a beautiful picture of a sailboat at sea. And the case is reverse of that of the pavement. We've got the cool air near the ground and the hot air above. And so light's going to come off the front of this boat. And as it comes to your eye, the light ray comes off. And again, if we imagine our tires, our wheels on the axle, here's the two tires. And we've got the pavement is up here. The mud is down here. So the bottom wheel gets snagged, and so rather than bending upward, the light wave bends downward and comes to your eye like this. And so then your brain traces it back, assuming that it came in a straight line, and you see the prow of the boat up in the air. And so we get this image of the boat. And it seems like there's this upside down mirage image of the boat in the air above. Examples of what a superior mirage might look like. We can see this coastline viewed from a boat. We see this upside down image of a mountain superimposed over top of it. Another example. This strange appearance. I can't say that I've ever seen one like this before. I've just read about them. But again, another great example of refraction.